All right, so in this video, we want to take a look at probability and what is called Bayes' theorem at the end of this section, a special theorem that deals with conditional probability. So a couple definitions. I'm not going to read those to you. Let's just jump in and take a look at some examples. And like always, we will just skip around and not necessarily work every single one, but kind of hit some of the highlights. So let's say that I roll a pair of dice and I want to compute several probabilities. First, the probability that I roll doubles. Well, there are 6 ways that I can roll doubles out of the 36 outcomes. And for most of these, I'm not going to reduce the fraction. You can if you want to. But for the sake of time, I'm just going to leave it in its unreduced form. The probability of not doubles. Well, since there are 6 doubles that I could possibly get, the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. There's 6 ways that I can roll doubles out of the 36 outcomes. When I roll a pair of dice, that means that there are 30 that are not doubles out of 36. The probability of a sum of 6. So how many ways can I get a sum of 6? Well, I could get a 1 and a 5. I could get a 2 and a 4. I could get a 3 and a 3. I could get a 4 and a 2. Or I could get a 5 and a 1. I believe that those are the only ways that I could roll a sum of 6. That's 1, 2, 3, 4, 5 ways that this can happen out of 36. Okay, a sum of 9 or greater. So 9 or greater would simply be a sum of 9 or a sum of 10 or a sum of 11 or a sum of 12, each of these right here. And so I would need to compute each of these sums individually and then add them up. A sum of 12, we'll start down here at the bottom or at the back end, is 1 out of 36. The only way that that can happen is double sixes. This would be 2 out of 36. This would be 3 out of 36. And 9 can happen 4 ways out of 36. If I add these up with the common denominator of 36, this comes out to be 10 out of 36. So yeah, example, rolling a pair of dice. Okay? Let's jump around. We'll do another example. This one is still probability. Okay? Remember, probability is just a part to a whole, numerator, denominator. Let's take a look at this example, and we'll use some combinations to do this one. A box has 100 bulbs, 10 are defective, and 90 are good. Okay? 4 bulbs are selected. Now, I'm gonna say that these are selected without replacement. What do I mean without replacement? That means I reach in, I grab a bulb, I test it, and then I reach in, I grab a different bulb, okay? So we're not testing the same bulb, perhaps, multiple times. So I want to find the probability that all of them are good. And you'll hear me say sometimes when I teach probability, make what you want to happen, happen. So I want to pull 4 good ones. Well, how many are good? 90 of them are good. And I want to select 4 of them. So from the 90 good, choose 4 of them to be selected out of, well, how many total outcomes are there for the sample space? From the 100 total bulbs, choose 4. So the idea is the probability that 4 of them are good is from the 90 good, choose 4, out of the 100 total, choose 4. And if I run this through, I get 0.6516 approximately, okay? Exactly 1 defective. So this would be the probability of 1 defective. Well, if I get 1 defective, then that implies that I got 3 of them that are good. So let's think about how this would be, okay? one defective. So I wish to get one defective. So from the 10 defectives, only choose one of them. Times from the 90 good bulbs, choose exactly 3 of them. Out of, okay, the denominator, this would be 100, choose 4. And if we run this through, we would get 0.2996. If I compute those 3 combinations and perform the operations. Okay? The probability of all 4 defective. So the probability that I get 4 defective. Okay, make what you want to happen. Well, from the 10 defectives, choose 4 of them over 100, choose 4. And if I run this through, I get 5.35 times 10 to the negative 5th power. If I move this decimal 5 times to the left, that's 0.000000535. So we would simply say it's highly unlikely that I will get all 4 defective. So here's an example where we can use combinations and sampling to compute probabilities. Let's do another one that is similar. We'll move down to this next example. Rupert has 8 silver dollars, 7 quarters, 5 dimes, 3 coins are selected at random. Find the probability of 3 silver dollars. Make what you want to happen. Okay, from the 8 silver dollars, choose 3 of them. Out of, okay, how many total coins are in the box? It looks like there's 20. So out of 20, choose 3. And for these right here, I'm just going to stop right there. I'm going to assume that you could compute these and find out what the probability is as an actual decimal. I guess I'll go ahead and do this first one. So 8 combination 3. In the TI, that's simply 8. Math, probability, combination 3. So 8 choose 3 is 56. The denominator was 20 choose 3. So 20 math, probability combination 3. So 56 out of 1140. So 56 out of 1140. So about 0.049 would be this probability right here. But yeah, like I said, for the next ones, I'm just going to leave it in their combination form. Okay, 3 quarters. Okay, very similar. So how many quarters are in the box? From the 7 quarters, choose 3 of them to select. Out of the 20 coins, choose 3. Exactly 1 of each. Okay, well, make what you want to happen. So from the 8 silver dollars, choose 1, times from the 7 quarters, choose 1, times from the 5 dimes, choose 1, out of how many total outcomes? From the 20 total coins, choose 3. Okay? And I'd multiply, I'd compute those combinations, get a numerator, get a denominator, divide it out, and get some answer. Okay, so let's think this through, okay? This next one, the probability of at least 1 silver dollar. Okay, so one of 2 things is going to happen. I'm either going to get at least 1 silver dollar or I'm going to get no silver dollars. So I would say the probability of at least 1 silver dollar would equal 1 minus the probability that I get no silver dollars. Okay, well, make what you want to happen happen. 1 minus, I want to get no silver dollars. Well, if I get no silver dollars, that means I only get quarters or nickels. So, how many quarters and nickels do I have? Well, that's 12. So from the 12 non-silver dollars, choose 3 of them, over from the 20 total coins, choose 3. And so the idea is right here, clean it up a little bit, I would compute this fraction, 12 choose 3 over 20 choose 3. This would give me the probability that I get no silver dollars, okay? And then subtract that from 1 to give the probability that I get at least 1 silver dollar. So I'll leave it to the student to actually punch that in and find out what that probability is. Okay? Alrighty, let me erase this and move on to a different page. Okay, lots of information on this slide right here that I want to bring to your attention. So a complement, okay, is what we just used to answer the previous question. So an event E plus its complement sums to 1. So a lot of times we can say the probability of the complement of E or not E simply equals 1 minus the probability of E. A couple of theorems right here. The probability of A or B or A union B is the probability of A plus the probability of B minus the probability of A and B. Okay, this should look similar to a theorem or an idea that we discussed back when we were introducing sets. Okay, mutually exclusive or disjoint events. This occurs when the intersection is the empty set. If the intersection is empty, then we say A and B have nothing in common, and so they are mutually exclusive or disjoint. If A and B are mutually exclusive, then the probability of their union, A or B, is simply the probability of A plus the probability of B. Now, in the same way that we have the inclusion-exclusion principle for sets, we also have it for probabilities. Okay, so the probability of A or B or C equals the probability of A plus the probability of B plus the probability of C. So I add the 3 individual probabilities together, subtract the probability of their pairwise intersections. What does that mean? That means subtract the probability of A and B, subtract the probability of A and C, subtract the probability of B and C, but then add their triple intersection. This would be the probability of A and B and C. So lots of important theorems, formulas, corollaries on this page right here. So let's move on and take a look at this example right here, back to drawing cards. Okay. A card is drawn from the deck. Consider an ace to be a high card. So it looks like I'm drawing from the standard deck of 52. So what about the probability of a king or a heart? So the probability of king union heart would equal the probability of a king plus the probability of a heart minus the probability of king and heart. Okay, so the probability of a king, this is 4 out of 52, plus a heart, that is 13 out of 52. Subtract probability king and heart, there is 1 king, that is also a heart, so 1 out of 52. And if I run this through, we should get 16 out of 52 for this probability. What about a king or a queen? Now it's my claim that these two are mutually exclusive or disjoint. So the probability of king or queen is simply the probability of king plus the probability of queen. Why am I not subtracting out the intersection? Well, my claim is that the intersection is empty because there is no card in the deck that is at the same time king and queen. So this would be 4 out of 52 plus 4 out of 52, so 8 out of 52. Like I said, you can reduce if you wish. Face card or a spade. So probability face union spade. So this would be face plus spade minus face and spade. Okay, so let's do the probability of a face card. Well, how many face cards are in the deck? That would be 12 out of 52 plus the probability of a spade. There are 13 out of 52 cards are spades, but there's a problem. I'm double counting. I have to subtract out the intersection. I have to subtract out the number of cards that are face cards and spades. Well, namely, there are 3 face cards that are also spades. So we subtract out 3 out of 52, which leaves us with 22 out of 52. Lastly, let's do the probability of a diamond or a card less than 7. So, probability of diamond union less than 7. Okay, so first, probability of a diamond. How many diamonds are in the deck? That's 13 out of 52. Plus the probability that a card is less than 7. Now let's think this through. I'm considering ace to be a high card. So what cards in the deck are less than 7? That's a 2, 3, 4, 5, or 6. So 2, 3, 4, 5, or 6. So that's 5 denominations are less than 7, but there are 4 suits of each. So 5 times 4 would give me 20 out of the 52 are less than 7. Subtract. I have to subtract out the intersection. How many diamonds are less than 7? Diamond and less than 7. Well, that would be the 2, 3, 4, 5, and 6 of diamonds. So that would be 2, 3, 4, 5, 6. 5 cards out of 52. And if I run this through, that is 28 out of 52. This is the probability that I get a diamond or a card less than 7. Okay, let's move on to something called conditional probability. So, the conditional probability of a given B is as follows. The probability of A, and this vertical bar right here is read given, the probability of A given B equals the probability of A and B divided by the probability of B. The piece that is given goes into the denominator. So let's use this definition to answer some questions from what we would call a two-way table or a contingency table or chart. So the following chart shows outcomes for 100 patients tested for disease XYZ. So we tested 100 patients, gave them a test to see if this specific disease is present. Now, the test is either going to result positive or negative, whereas the patient will either have the disease or the disease will be absent. So, let's ask, what's the probability that the disease was present given that the patient tested positive? So this would be probability present given positive. Okay, well, this would be present and positive over the piece that's given goes in the denominator, positive. So I almost always start with the denominator first when I look at these conditional probabilities. So ask yourself how many total people tested positive. That would be 52. Now, of these 52, how many of them tested, how many of them was the disease actually present? That would be 49. So 49 out of 52. And we would call this 49 out of 52, okay? Just so you know, we would call this a true positive. If the disease is present, we want the test to test positive. B, disease present given the patient tested negative. So probability present given negative would be present and negative over the piece that's given goes in the bottom, so negative. Okay, so how many total people tested negative? That would be 48. And of these 48, okay, how many was the disease present? That would be a 2. Okay? So 2 out of 48. This is disease present given that the patient tested negative. We would call this right here a false negative. Tested positive given that the disease was absent. Okay. Probability tested positive given that the disease was absent. This is positive and absent over absent. Okay. How many total people was the disease absent? Well, the disease was absent in a total of 49 individuals. Of those 49, how many tested positive? This would be what? 3. Okay. What about tested positive or the disease was present? Okay, how could we do that one right there? So the probability of positive, the clue right here is or, so union present would equal positive plus present subtract positive and present. Okay, how many people tested positive? That would be what? 52. Plus, how many was the disease present? That is 51. Subtract positive and present. That would be 49. So 52 plus 51 minus 49 gives us 54 out of 100 total. So this is the probability that someone tested positive or the disease was present. Okay, let's move on, and we'll talk about independence, dependence. If events are independent, then the probability of A and B is the probability of A times the probability of B. If events are dependent, then the probability of A and B is the probability of A given B times the probability of B. So let's take a look at a couple of examples for this next one. A die is rolled thrice. Find the probability of rolling 3 sixes in succession. So let's take a look. The probability of 3 sixes, so that'd be a 6 on the first, a 6 on the second, a 6 on the third. This would be 1/6 times 1/6 times 1/6. Each die roll is independent of the others. So this would simply be 1/6 to the third power, or 1/216. A coin is flipped twice. Find the probability of tossing 2 heads in succession. So the probability of HH, I'm flipping it twice. So this is 1/2 times 1/2, or 1/2 squared, that is 1/4. Okay. We'll skip C, move on to D. A box contains 8 donuts and 4 kolaches. You reach in and grab 3 items without replacement. Now this is important right here. Anytime I sample without replacement, the events become dependent. So I want to ask, what's the probability that all 3 are donuts? So the probability of donut, donut, donut. Okay, make what you want to happen. You want the first one to be a donut. So that would be 8 out of 12. Now, how can I guarantee that I'm sampling without replacement? Well, I could eat the donut. Now I want to reach in and I want to grab a second one. I want it to be a donut. Well, there are 7 donuts that remain out of the 11 items in the box. And now I want to reach in and grab a third item and I want it to be a donut. Well, only 6 donuts remain out of the 10 that are in the box. And I need to multiply these together. And if I multiply them together and reduce, we would get 14 out of 55. This is an example of a dependent probability. Okay, let's move on, and we will discuss something called Bayes' theorem. So Bayes' theorem is stated as follows. It says the probability of A given B, as we know, is the probability of A and B over the probability of B. Well, I can write the probability of A given B as the probability of B given A times the probability of A. Now, the probability of A given B is a conditional probability. It is called the posterior probability of A given B. The probability of B given A is also a conditional probability. This is the probability of B occurring given that A is true. The probability of A and the probability of B are the probabilities of observing A and B respectively without any given conditions. These are called the prior probabilities. Now, we can extend Bayes' theorem to any number of events. So here is the generalized form of Bayes' theorem. And I'm not going to read all of that to you, but we're just going to jump in and take a look at an example where we might use Bayes' theorem. So, a tire and auto shop purchases tires from 3 different manufacturers and tracks how many are defective. Consider the information compiled below. So, I have some tires that come from manufacturer A, some tires come from manufacturer B, and some come from C. In essence, if I take a look, 0.5 is the fraction that come from A. So 50% come from A, 20% come from B, and 30% come from C. Now, each manufacturer has its own different rate of defectives. So 0.01 tires that come from A are defective, or a 1% defective rate. 0.04 tires that come from B, or a 4% defective rate from manufacturer B. And 0.02, or 2%, of those that come from C are defective. So let's use this information along with Bayes' theorem to answer the following. A tire selected is found to be defective. The question we wish to ask is, what is the probability that the tire came from Apollo? So, the probability that it came from A, given that it was defective, would be the probability that it was defective given A times the probability of A over the probability of defective given A times the probability of A plus the probability that it was defective given B times the probability of B plus the probability that it was defective given C times the probability of C. So let's compute this numerator. The probability that it was defective given A times the probability of A, well, that is simply 0.01 times 0.5 over 0.01 times 0.5 plus the probability defective given B times B. Okay, that would be 0.04 times 0.2 plus the probability defective given C times C. This would be 0.02 times 0.3. Now, if I compute this numerator, 0.01 times 0.5, I get 0.005 over, and I'm going to compute this denominator out quickly. So this would be 0.01 times 0.5 plus 0.04 times 0.2 plus 0.02 times 0.3. I get this 0.019. So this is my number that's in the denominator. And I'm gonna put this number in a red box because we're gonna see him appear often. And now I need to divide these out. So 0.005 divided by 0.019. So I get, 0.263. If I go 3 decimal places, that's 0.263. This is the probability that it came from Apollo. Okay, what about the probability that it came from Bridgestone? Okay, so this would be very similar. You're going to see a pattern develop with Bayes' theorem. The probability of B given defective. Okay, the probability B given defective would be the probability of defective given B times the probability of B over the probability of defective given A times the probability of A plus the probability of defective given B times the probability of B plus the probability of defective given C times the probability of C. if you take a look, this is why I said to consider that number in this red box. The denominator right here stays the same. So this denominator is still going to be 0.019. And in the numerator, it's defective given B times probability of B. This would be a 0.04 times a 0.2. So if I multiply those out, I get 0.008 over 0.019. And if I'll divide that out, I'll get 0.421 approximately. I'll write that up here, 0.421. So if a tire was found to be defective, the probability that it came from Bridgestone is 0.421. Okay, lastly, the probability that it came from Continental. So this would be the probability C given defective. So to save time and space, instead of writing everything out, we know that this denominator is going to be this 0.019 again. And in the numerator, this is simply the probability that it is defective given C times the probability of C. So this would be 0.02 times 0.3 divided by 0.019. And if we divide all of that out, we get 0.316. So this is the probability that the tire came from Continental. Now, I want to ask this question. If I were to add the probabilities of A, B, and C together, hopefully you would see that it sums up to be 1. Why is that? Well, the tire either came from Apollo, Bridgestone, or Continental. And so when I sum up these 3 probabilities, they're going to sum up to be 1. So let's keep this in mind, and we'll explore this just a little bit more. So let's consider a tree diagram as follows. Okay. So .05 come from A. 0.2 come from B, and 0.3 come from C. So 50% of my tires come from company A, 20% from B, and 30% from C. Now, A has its own rate of defectives. Its own rate of defectives are 0.01 are defective, and that means 0.99 of them are good. Now, if I do the same thing for the other 2 companies, for company B, some of them are defective, some of them are good. Well, for company B, 0.04 are defective, which means 0.96 of them are good. And from company C, either defective or good. So this would be 0.02 or 0.98. Now, what I'm going to do is I'm going to multiply each of these numbers through the tree diagram. Meaning, if I go 0.5 times 0.01, so 0.5 times 0.01, I would get 0.005. Okay? what is this? This is the probability, okay, that it is defective and from A. What if I did 0.5 times 0.99? So 0.5 times 0.99. This would be 0.495. That's this number times this number right here. Okay. So I'm going to continue these down. If I go 0.2 times 0.04, 0.2 times 0.04, that's 0.0008. And then if I did 0.2 times 0.96, that would be 0.192. If I did 0.3 times 0.02, I would get 0.006. And if I did 0.3 times 0.98, I would get 0.294. Now, I'm going to underline these right here. These are the respective defective probabilities coming from their respective companies. And in blue right here, 0.495, 0.192, and 0.294 are the respective probabilities that the tire is good. So let's say that a tire is selected at random, and I don't know what company it came from. Well, let's find the probability that the tire is defective. Well, this is fairly straightforward. The probability that it is defective is simply 0.005 plus 0.008 plus 0.006. And if I add these together, I get 0.019. Now, this number right here shouldn't come as a shocker. Okay? What number was this? This was the denominator in the previous part of the problem. This was the probability that the tire was defective. Now, what's the probability that the tire is good? Well, this would be 0.495 plus 0.192 plus 0.294. If I sum up these right here, we would get 0.981. So what are we trying to say? We are simply saying that for this given auto shop, 98.1% of our total tires are good, and only 1.9% of our tires, irrespective of which manufacturer they come from, are defective. So if I select a tire at random from this auto repair tire shop, there's a 98.1% chance it's going to be good and only a 1.9% chance that it's going to be bad. So that will conclude our lesson on probability and Bayes' theorem.